So we want to start talking about, when we've been talking about AX equal to B, it's typically been in relationship to this stream function solving from the vorticity. So we show that the Poisson equation generates a large AX equal to B. And so I want to talk about some of the practical implications of this when you start to implement these things numerically. And I want to not only talk about how we might solve it with the FFT, how we might solve it also more rapidly with iterative schemes, and how would we represent this matrix A under discretization that is largely zeros, is very sparse. And in fact, just because scientific computing typically generates this, we are often working with very sparse matrices. So it's important to take advantage of that in terms of the memory footprint as well. So I'm going to show you all of these things in terms of comparing and overcoming some of the computational difficulties we're going to encounter when we solve realistic problems. Not even ones that are that hard. These are just things we're going to have to deal with immediately as we start to solve any kind of problem at all. Okay, so first of all, I want to start off with the Fourier transform and the usage of the Fourier transform and some of the issues that we have right away and how we would take a derivative of it, because that's exactly what we're going to have to do in context of this Poisson equation we want to solve. So first of all, let's build a function and think about taking an FFT. So it's kind of as simple as this. Here you go. We define a domain. We're going to find a domain size 20. We're going to have 128 points. And since it's periodic boundary conditions, this is very important. So I define a domain with n plus 1 points. But the last point is the same as the first because it's periodic boundary conditions. So I can remove it. And that's exactly what I've done right here. Okay? That's an important step. You don't solve for the same point over again. You have the first n points, and the n plus 1 point is the first point. Okay, that's what it means to have the periodic boundary conditions. And what I'm going to do here is take a function. Here the function is given by just a Gaussian. And then just FFT it. And as simple as this, np fft.fft function, I have it. There's one other command you want to know. So once I've done that, I'm in the Fourier domain. And if you want to inverse Fourier transform, you just IFFT. Okay? But I also have this function here. You're probably wondering, like, well, what's FFT shift? Well, I'm going to show you that in a minute. Because one of the things that happens, if we look carefully at the FFT algorithm, it does what's called a butterfly sort of algorithm, in which the structure of this is to intermix the points. It turns a problem of size n into two problems of size n over 2, to 4 problems of size n over 4, to 8 problems of size n over 8, all the way to its n problems of size 1 by 1. And so that's how this n log n algorithm works. It turns this problem into a bunch of 1 by 1s, which then get glued back together through this butterfly type architecture. I'm not going to go into detail that now, but it does have a practical impact on what you're doing with the FFT. In particular, if you take the FFT, here's the Gaussian that we took FFT of. The FFT of a Gaussian is a Gaussian, but of course when I take the FFT, this is what I get. It doesn't look like a Gaussian at all, right? You get these edges with large oscillations. And in fact, this is simply due a consequence of that butterfly algorithm that we have for the FFT. So if what the FFT shift does is it brings it back to this representation here, and then what we do, instead of essentially the FFT also multiplies every other one by -1, so if we were just looking at the absolute value of it, it becomes the Gaussian that we would expect. So in other words, wrapped up in the FFT is, if you want to look at the FFT data in the Fourier domain, it's not in the way you would have it structured. The wave numbers get shifted like this. And so you have to have that in mind when you're working in the FFT domain. And the reason they don't shift it back is because it costs computational time. The whole idea of this is to go as fast as possible with your computational algorithm. And so it's not going to do this for you because that's costing overhead and computational time. It's going to leave like here, and then you have to understand that when you take an FFT, it assumes you're in a 2-pi periodic domain and it's doing this to your data, and you're in the shifted domain. So you, remember, I'm going to emphasize this again. If you're doing scientific computing, your number one job is to be the manager of your algorithm. A lot of the underlying stuff the algorithms built in are going to take care of it for you. But if you're not organized about understanding what's happening in your code, like for instance, if you use FFT that this is happening, you're going to be in trouble when you try to solve this. Same thing with making sure you've organized your data correctly and that you have the right differentiation matrices. This is all very important from an administrative point of view of getting the code correctly done. So let's talk about then one of the most important results of FFT. In addition to the n log n speed, you have this derivative relationship here. So if you take the nth derivative of something, all you have to do is multiply in the Fourier domain by ik to the nth power, and then inverse Fourier transform, and you have the derivative. So let's compute some derivatives. Let's actually use this in practice. I'm going to show you this in practice, how to do this. And here's a little code that's going to do it. First, I'm going to define a domain, size 20, 128 points, a linear space. It goes negative L over 2 to L over 2 in n plus 1 points. And I just take out the first n points. Remember, the last point is the same as the first. I'm going to define two functions, hyperbolic secant, hyperbolic tangent, because in fact we're going to differentiate hyperbolic secant, which we can actually write down analytic solution techniques for the first derivative, second derivative, third derivative, and so forth. And we're going to compare our method to the exact derivatives that we can compute, okay? And so here's what we're going to do. We're going to take this, here's my function, and we're going to FFT it. That's called UT. So just NP FFT, FFT U. I'm now in the Fourier domain. So all I have to do is apply this formula. Once I'm in the Fourier domain, all I have to do is multiply by IK. Okay, so how do I define K? Well, couple very important assumptions. The FFT thinks that you're working on a 2 pi periodic domain. But notice, I structured my entire algorithm to be on a domain that's size L. So to take into account the scaling difference between the 2 pi and your L, here it is right here. There's a 2 pi over L multiplication that goes on right here. This is a scaling factor so that if you work on a domain size L, this scales it down to 2 pi. What you're seeing here now are the wave numbers. In other words, when you do Fourier transform, you represent in terms of e to the ikx, where it's like, you know, cosine 1x, cosine 2x, cosine 3x. Those are the integers that you have, and that's what these are here, except for you understand that you did this. You did this thing when you did the butterfly flipping, and so the range goes from 0 to n over 2, and then minus n over 2 back to 0. So this is the flip that you have. FFT shift undoes it, but we're going to use this because when we take derivatives, when we FFT, it assumes that we're in the shifted frame, and so we're going to use this as our wave numbers. And so to compute derivatives, here's how easy it is. First derivative, multiply by ik times ut. Second derivative, negative k squared times ut. Third derivative, ik cubed, right? And then you just invert these. Just do it. Inverse Fourier transform, which is FFT.IFFT, and you're back in real space. That's as simple as it gets, and in fact this is one of the most accurate way to compute derivatives if you have periodic boundary conditions. Okay? So anytime you have periodic boundary conditions, you should definitely always be thinking about using a Fourier transform. So here are the comparisons. The original function is this blue here, so it's just a Gaussian. And then you start seeing, for instance, the first derivative is in pink here, and we've plotted directly on there the dots, which are the exact solution, and then the approximation, which is a line, and the second and third derivative there as well. In fact, these are highly accurate derivatives for these functions. And so what you have here is a very simple way to produce derivatives. With an FFT, assuming that you have boundary conditions, this is about the fastest way you can do a derivative and one of the most accurate ways you can do a derivative as well. Okay? And this shows it. So this is, again, you can download all of this from my GitHub and run through all of this code. So you just have it there for you to play around with. So let's move on to sparse matrices. So that's one of the issues, is how do I do derivatives practically with the FFT? Another is, how do I represent matrices like this? It's mostly zeros. So just think about the memory constraints. If this is an n by n matrix, then memory-wise, I'd have to save order n squared to keep this matrix A in memory. But you notice it's almost all zeros. In fact, there's only 9 diagonals on this matrix that matter. So really, I should have 9 times n is all I need to keep to represent this matrix. By the way, for a long time in scientific computing people know this. They want to have a small memory footprint and make use of the fact that most differentiation matrices are massively sparse. And so they've invented an entire framework to represent these data matrices. So I want to start building this out in a code base. So for instance, this is a top view of that matrix where only the non-zero elements show up as white. So that's the structure of the matrix that you have. And so what we want to do is, how do I build this matrix and only keep the non-zero components in memory? Okay? And you can do this with sparse diagonals. So you can bring this in, import from SciPy, sparse, import sparse diags. And what this is going to allow us to do is have this infrastructure for sparsity there. Now, I'm going to do a very simple example of the matrix I just showed you, right, which is this one here, which what I did is I assumed I have 5 points in X, 5 in Y, which is not nearly enough, but it's just for illustrative purposes. But it's a 5 by 5, this becomes a 25 by 25 matrix. And so it's 5 points in X, 5 points in Y, so the total matrix is going to be that squared. And here's how you would do it. So first of all, I mostly have diagonals that either have ones on the diagonals or occasional ones or occasional zeros. So in fact, this structure of this matrix, you really have to study it, to see where, for instance, on this off diagonal, it's mostly ones with an occasional zero. Mostly ones with an occasional zero. And over here, you get a 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, so forth. So building this matrix, I've said this before, that you have to understand how this matrix is built. This came directly as a consequence of the discretization and X and Y with periodic boundary conditions. That was in the first lecture in this series. And so it is really important. Your entire job really is to organize this matrix. Because once you have it, the rest is going to be very easy for us to do. And here's how you build this matrix though, right? You would start saying, okay, I first got to deal with vectors that are mostly ones and then zero, ones and zeros. So I build these all up in here. And this is exactly what this is doing. So every nth point I put a 0 or I put a 1 depending on if I have a 0 or 1 matrix. And so I'm going to build all of these. These are going to be my diagonal elements. My 9 diagonals I'm going to lay down in that matrix. And how do I put them down there? Is now I use this, essentially this SPDIX framework. So first of all, where are the diagonals? These are what the diagonals are. These are the matrices that are going to be in the diagonals. And you can verify for yourself where they're going to be. And this is going to be where they're positioned. So the 0 position is the main diagonal. This is above the diagonal, this is below the diagonal. So one above the diagonal, I'm going to put, so on the diagonal 0, I put -4s. One above the diagonal is essentially going to be this matrix E3. One below is this E2. And you can look, we just built them. And then SPDIAG says, tell me what you're putting on, where you're putting it on, and the size of this matrix. This is the entire solution technique here. And what this builds for you is it builds a sparse diagonal matrix with 9 entries. It is really critical you know how to build this. This is, in fact, the entire solution technique, del squared psi equals omega, your job is to understand how this matrix is built. Because once you have it, then it's really easy to solve from there. But if you don't know how to build this, you don't really know how to solve this. Again, we have to switch your mindset of thinking about you are a manager of the data, and your job is to understand how you're basically putting all your data together in a compact way, because the rest of it's just going to be AX equal to B. So that's how we do a sparse model. Last thing I want to cover is, again, so we've got the FFT for fast solves, sparse representation. The last thing we want to talk about is, what about the iterative solvers that are sort of kind of higher end? And a lot of these are built in directly into scikit-learn, or into Python and SciPy. And so I want to go through some of these because they're commonly used. They are used everywhere in practice for large-scale computing as a fast and efficient way to solve these AX equal to B problems. So I'm just going to introduce 2 of them, GMRes and BiCG stabs, which are sort of common, but there's others that are out there. And essentially what it is, you're going to call in from the sparse linear algebra package, and notice that it's capable of using sparse representations of matrices. But all you do is say the solution X is GMRes AB. So it's AX equal to B, you give me the A and the B, solve. That's it. So the blend above is you're actually, notice this is coming from the sparse linear algebra package, and you bring in GMRes, or you bring in BiCG stab, and you just give me the A and the B, and this thing will actually use these advanced iteration techniques to solve your problem directly, that AX equal B, in an efficient manner. And the goal with these is to beat order n squared, right? LU decomposition is going to be your baseline target of what you got to beat, which is n squared. And n squared is a lot to pay. FFT is n log n. And if you can do an FFT, you do an FFT. But sometimes the boundary conditions aren't amenable to the FFT, so you want to try to use something like this. And by the way, these algorithms have a lot of different things you can bring in, a lot of flags. You can specify how accurate you want it to be. You have to specify the number of iterations, preconditioning matrices, the initial guess vector. You always want to initially guess it. When you're time stepping, if you don't give it a guess, it just starts off with a guess of zeros. But what you want to do is say, well, if I'm solving the solution in the future is not that big of a change from what it is right now, so I'll use the current value of my stream function, for instance, as the guess for the future, which is only delta t into the future, and that will really cut down the number of iterations. If you don't do this, it's a stupid way to solve it. So you want to use this. Always use the x0. You can restart it and so forth. So a lot of optionality with these codes. These are very sophisticated. We're not going to go into detail of how they're actually structured and work, but they are available to you really easily, just like the FFT. One line of code, and you have all the power of this methodology available to you to solve fairly sophisticated problems that arise, like the AX equal to B we have for solving that stream function equation. So that's kind of it. These are really practical tips of things you actually have to think about. These aren't just esoteric. They're like every day. If you're going to use FFT, if you're going to represent these discretization matrices in sparse form, and if you're going to use some higher end iterative schemes to beat the order n squared bottleneck of a computational algorithm. All these are not, again, not esoteric. They're like generic things that you have to be considering for every time you start thinking about any kind of serious PDE solvers that you're going to be using in general.